Now I have to live up to that introduction. Well, thank you for hosting me, and thank you everyone for coming. So today's talk is going to be a little bit experimental in that I'm really going to tell you about two different things, but I hope to share a question with you that brings the topics together. So I'm going to talk about work that I did with Alan Guth and with Mark Hertzberg. And so the archive paper is here. It was also actually an editor's suggestion in PRD in the fall. And also work that I've been doing with Professor David Kaiser at MIT, along with Evangelos Fakianakis, who is now a postdoc at UIUC, along with two incredibly talented undergraduates, Matt DeCross and Ani Prabhu. So we have one paper up on the archive about this, and maybe we will have a second one coming soon. So actually, I should mention what I'm going to talk to you about today, partly from this work. I'm actually going to tell you about the things that are in the paper that haven't come out yet, and you are the first research institute to hear the work. So this is, I guess, the post-APS premiere. So even though I'm going to talk about dark matter and then I'm going to talk about things relating to inflation, really the question that ties these things together for me is how can new approaches to quantum fields illuminate evolution of the universe on all scales? So this is the question that I'm very interested in, both from an astrophysical perspective and from a physical perspective. So I don't really see the distinction between those two things that other people often draw. So this is one way of putting it in words. Another way of putting it is that we have this incredibly gorgeous map of the early universe, or early-ish universe, depending on how you put it. This is the Planck map. And so what we're seeing here is that to 1 part in 10 to the minus 5, everything looks about the same in every direction that you go in. But there are these anisotropies. And what we're really seeing here is the seeds of structure formation. So another way of putting the two things that I'm going to talk about is really, where do particles come from? And how can we understand that from a particle physics perspective, as well as from the point of view of the questions that we ask in astrophysics? So as was mentioned, I have a long-standing interest in what the quantum gravitational picture is here. So is particle production inextricably tied to space-time at the quantum gravitational level? I'm not really going to get into that today, but I'm here until Thursday morning, so I'm happy to talk to anyone about that later. So for the people in the room who are not field theorists, I just kind of wanted to give a normalization of what I mean when I talk about a particle. So one way to think about particles is that they are excitations of fields that are pervasive in the universe. So another way of asking the question of where do particles come from, what seeds structure formation, where did the structures that many of us in the room study come from, is to ask, how did fields get so excited that these excitations led to the formation of the structures that lead to us sitting here in this room? So you probably don't often think, oh, where did everything come from? Clearly it came from the inflaton. But this is one of the ways that I think about this question. So this is an era of rapid expansion that was driven by a particle called the inflaton. So I think many of you know what inflation is, but I just wanted to normalize my use of the word inflaton there. And so importantly, we often talk about inflation. We talk about the things that inflation does for us. It helps us get the homogeneous isotropic universe that we have been observing. But maybe the inflaton can do other things for us too. And so I think that we are sometimes inattentive to the inflaton in its elder era. And so it's important to note that even after inflation ends, the inflaton is oscillating in its potential, right? So it doesn't just like poof, disappear. There is still potential energy in the inflaton field. So a question that we can ask and should ask is, what does it mean to recover from inflation? What happens in that era immediately after inflation? So this is an era, oh, I put the parentheses wrong. So this is an era known as reheating. The era of reheating that I've been particularly interested in is preheating. So this is a very nice picture of the energetic history of the universe from this very nice paper by Lineweaver. And so you can see, so something happens here. There's lots of debate about what came before inflation. So I like this trans-Planckian unknown, we don't know. So inflation happens, we have the temperature of the universe here, we have the energy here, time after Big Bang coming towards us here. Inflation happens, and the universe rapidly expands, and presumably also cools off in that time period. Somehow, the temperature needs to get back up so that baryogenesis can occur. So this is an era that is not very well understood. We call it the reheating era. I like to think about it actually in terms of a thermodynamic question of what is the temperature history of the universe, and in particular in that time period. But it is also often thought about as a question of how do you produce particles that will then participate in baryogenesis. So in some sense, this is really, if there's any particular point in the timeline that you could say is the era of the standard model, this is the era where the standard model really takes off. And so preheating is really the very beginning of this. And so a question that you can ask is what can we get from the inflaton? And so something that you could potentially get from the inflaton is parametric resonance through coupling between the inflaton and other matter fields. And so this is what, if you go through the literature, this is what people really mean when they talk about preheating. And then, so the essential timeline is that eventually you want to thermalize to the radiation-dominated era. And so in terms of what are things that we are trying to achieve when we are thinking about doing models of preheating, the ultimate goal and ideal is to be able to calculate a thermalization temperature that will tell us exactly what this point on the chart is, right? So this is an era that is not very well understood, both from a theoretical standpoint and even from an observational standpoint. We are not really sure how to get at it, or if it's even possible whether we can get at it. But I try to be an optimistic. I refuse to accept that there are parts of the universe that aren't accessible to us yet, inside our horizon anyway. So I like to think that maybe there's still an observable out there. So I put that maybe to people in the room that that's something that we can all think about. OK, so what I have been particularly interested in is we think about the inflaton as one field. It's one particle is a way that you can think about it. But what we're really interested in is the dynamics of not just one particle, but the inflaton with other particles, with other fields. And so immediately you are forced to start asking questions about multi-field situations. So that's preparation for this. I try not to overwhelm people with equations, so I just want to say you are not required to understand in any great detail what's on this slide. And this is really for the equation lovers in the room. There's a graphical one coming next. So the important thing is this is the action that you can write down for a non-minimally coupled multi-field system. And so non-minimal coupling means that you have an unusual coupling between the field and the curvature. So this is one particular type of system that we are interested in studying. And you can be motivated by a few different things. One, if you're a math nerd, this is just really fun to play with. There's another reason, actually, which is that renormalization group calculations sort of suggest that maybe we need terms that look like this one in the equations of motion. But so what's interesting and highly annoying about this equation, and this is really the important thing, is that it doesn't look like the Einstein action. And so it's fairly inconvenient to calculate with. It turns out that we can do a conformal transformation. So this is really kind of a fancy coordinate transformation that will allow us to bring the action into an Einstein-like form. And so really what I want you to take away from this is that we can start with this kind of complicated picture, make it a little bit more like what we are familiar with for doing calculations, but this involves making changes to the potential of the field that we are dealing with. And this actually turns out to have significant impact on the physics that we get out of it. So it really does matter whether you were talking about a system that has this F term in front of the R, or doesn't have the F term in front of the R. It makes a real physical difference. Okay, so that was with equations. So put more simply in graphical terms, in the Jordan frame, you can have a potential that looks like this when you conformally transform to the Einstein frame so that the equations of motion look more familiar. Then your potential starts to look like this. And so what you're seeing is actually that the potential is going to be stretched by the presence of this conformal transformation. So there are various things I could say about this if I wanted to give an extremely technical talk. But one of the fun things for my fellow math nerds in the room is that part of what you get out of this picture is an artifice of field space that mirrors general relativity perfectly. It's quite beautiful. And that field space actually has a real physical impact. And so what I mean by that, just to back up, is you see this capital G right here, that is actually a metric on the field space of whatever n number of fields that you have. And there's some really nice papers about this by David Kaiser that I recommend reading, and Edward Mazenk, who's a former student and now a graduate student at Stanford, I believe. So just to kind of give an overview of what was in our first paper, where we were kind of exploring these non-minimally coupled systems, if you take an inflaton field and treat it as a background field, the oscillations of the background field are actually going to be affected by the conformal stretching of the fields in the frame. So when I say that this field space has real physical impact, that's the kind of thing that I'm talking about, is the behavior of the background fields is actually different. So you can also look for systems that we call the single field attractor. And this is a system where it behaves as if it is a single field. But it is actually going to display different behavior from a system where there's actually only one field. And you see this with the perturbations. I'm going to show more about that in a second. But the takeaway point is that you're going to get enhanced efficiency of preheating. And this really highlights why you would want to study a system like this. In addition to the motivation of renormalization groups sort of suggest to us that maybe we should consider these additional terms, is that we're constantly looking for what is an inflation model that will efficiently allow us to preheat. Should we find an inflation model that can create a nice preheating and reheating picture, that's motivation to further explore that inflationary picture, because it does something that we need to fill in our cosmic timeline. So something that I'm not really going to talk about, but I just wanted to add for the sake of completeness, is that the effective mass for the perturbations is going to be different than you would expect in a single field picture. And in a minimally coupled picture as well. Okay, so there's a lot happening right here. But what I want to say is that the strength of the non-minimal coupling, so the strength of that stretching, that conformal stretching that occurs, definitely affects the resonances. So you can see that there are going to be much stronger resonances when this C, which really measures the strength of the non-minimally coupling, is stronger. So the other thing to take away, besides the fact that you have a stronger resonance here, is that as you get to high values of C, these lines, which measure the strength of the resonances, start to lay on top of each other. And so we start to see an attractor behavior where once you get to a certain value of non-minimal coupling, this system starts to look very similar. So there's a clear asymptote. And so that's an interesting phenomenon that we did not really expect to see when we went into this. And so this was one of the interesting products. And so this is the case with adiabatic modes. So you'll see that the picture with isocurvature modes is actually quite different. So here, these are all in the strong non-minimal coupling limit. And these are for different wave bands. But what you find here is that you don't actually see these resonances laying on top of each other. And so we don't see the same kind of asymptotic behavior. And this is a fairly new result, so we are still kind of exploring what exactly is happening here. So I'll mention that one way that this could end very badly is that it could suggest that we should have very strong non-Gaussianities, which at this point in time we really don't really want. Okay. So just some concluding thoughts on preheating. The takeaway should really be that the adiabatic modes and isocurvature modes have completely different behaviors. And so there is something to explore there. We see strong resonances with the isocurvature modes. And so I think really the most compelling thing here is that we see a strong case for studying non-minimally coupled pictures, in addition to the motivation that comes to us from particle physics. And since I'm at an Institute for Theoretical Astrophysics, I will mention some vague things about observables. I think that the big thing really is that this is an area where we need more people to be thinking creatively and actively about how to go after information from this time period in the very early universe between inflation and the beginning of baryogenesis. So one potential thing that could come out of LSST or even out of Euclid is perhaps there are some higher order imprints that you could see on structure formation. Of course, using 21 centimeter data, you may be able to characterize the shape of the inflaton more, and this might give us some hints about our inflationary model. And of course, we're always constantly interested in what we can get out of B modes and optimistic about what we can get out of B modes. So that's kind of, I think it's very exciting work, partly because it's very mathematical and it's a lot of really fun calculus. But I also think it's an interesting question that when I've given like little 10-minute lunch talks about this, I usually say, preheating, what is it and why should you care? So I think we should care because A, it's an exciting thing that we don't really understand, and that's what we do. And I think that we should be able to figure it out. Okay. So moving on to axions, from inflatons to axions. When I was finishing my freshman year of college in 2000, I was a summer research student on the collider detector Fermilab experiment. And I went to see Rocky Kolb give a talk. And so this was 2000. We had just discovered cosmic acceleration. Everybody was pretty excited about it. And Rocky gave this talk that could have been a little bit depressing for a 17-year-old. So he said, well, we're at a very exciting moment in cosmological research. We've pretty much figured out what everything in the universe is made of. We know that it's about 3/4 dark energy. We know it's about 1/4 dark matter. And a smidgen of it is the everyday stuff. So we're right around the corner. Just as soon as we figure out what dark energy and dark matter are, we will be done. And I'm very happy that 16 years later, none of that has been worked out because it has given me things to do, and I think probably several of us have things to do, thankfully. So as was mentioned, I've been very interested in the dark energy question. But as a postdoc, actually, I sort of accidentally stumbled into working on a dark matter question that I now actually find more compelling and exciting. So I'm going to start by telling you the question we ended up asking and the answer we ended up coming up with. And hopefully, by the time I'm done with this section, both the question and the answer will make sense to you. So an interesting question that is being broadly asked in the literature is, does axion dark matter form Bose-Einstein condensates? So we think the answer is yes, in small, locally correlated clumps, such as Bose stars. And it's important, the small, the locally correlated part. The Bose stars thing is a matter of nomenclature, and I'll get to that in a bit. So I like to start by reminding myself and others of what the case for dark matter actually is. So this really comes down to looking at the rotation curves of galaxies and looking at the kinematic data and backtracking from that and figuring out how much luminous matter we would expect to be in the galaxy, and then comparing that to the luminous matter that we actually see and noticing a discrepancy, right? And so this is really, we apparently need more mass than we can see because there is a discrepancy between luminous matter and the kinematic behavior of galaxies. So of course we could ask, is this modified gravity? I actually think that that is still an interesting question. I've seen some creative work, say from Sofia Cisneros, who's at UMass Boston. But really what we're talking about is something that doesn't produce light. And what I'm getting at is that we often kind of tell the public that dark matter is dark matter because it only interacts through gravity. And this is not quite correct, we hope, anyway. What we do know about it is its only significant interaction is with gravity, but that doesn't mean it can't have other interactions. And this is actually pretty important for detection, right? So we have zero hope of direct detection of dark matter if it turns out that its only interaction is with gravity. So we kind of hope that it's not. And I like to emphasize this partly because the Axion could have some interesting phenomenology that relies on it having other interactions besides gravity. So all of that said, all of the data over the years has indicated to us that we need some beyond the standard model solutions, some new particle physics. And over the years, theorists have come up with a couple of ideas about this. So this is made by Tim Tate, and it is the Venn diagram to end all Venn diagrams. This is the greatest Venn. You're never going to see a greater Venn diagram than this one, except for maybe an updated version of this Venn diagram. So you can see a lot of the ideas that people have had over the years. So there are a bunch of things that fall under supersymmetry. There are things that intersect with supersymmetry, but are not always supersymmetry. The poor little Higgs has been asked to do pretty much everything we could possibly want in particle physics. We want it to drive inflation. We want it to drive reheating. Now we want it to be the dark matter as well. So you also see sterile neutrinos on here. So that is not a neutrino that we have seen, but it is one that people are looking for, so that's still very much on the table. There's a lot of stuff happening here. So there's also this corner, Axion-like particles. So that's down here. And I just want to make a comment about the nomenclature as you may go through the literature. Axion-like particle can mean a lot of things. Many, many, many things. It can mean something that is like the axion, and it can just really mean it's a scalar particle, and those are often used interchangeably. And one reason that I want to be clear about this is because I know that when this talk is over, everyone's going to drop all of their research programs and decide to work on axions instead. And you're going to look things up, and you're going to find stuff that talks about axion-like particles. And it's going to say things that contradict what I say. And you're going to be like, wow, that was a bad talk. But actually, it's really just that we are not always careful in the literature. So I just want you to, when you are reconfiguring your research program, beware the difference between the axion and the axion-like particle. And so you'll notice there's this thing, QCD axion. So what's that? It's a dark matter candidate. And really what that comes down to is it has a small mass. It has mostly gravitational interactions. We expect that in the fairly early universe where it becomes important and would dominate as a dark matter candidate, that it's non-relativistic, so it's cold, as we would expect dark matter to be. But the nice thing about the QCD axion, so by QCD, this is indeed quantum chromodynamics, is that it's a twofer. Because in fact, the axion was first invented, or it's really the byproduct of the best solution to the strong CP problem. So the strong CP problem is essentially that you can write down terms in the standard model that should break CP symmetry, but this breaking has never been experimentally observed. So Helen Quinn and Roberto Pecci came up with something that's called the Pecci-Quinn mechanism in order to resolve this problem. And a couple months after their paper came out, they got a phone call from Frank Wilczek, who said, you guys know that there is a particle in your model. There's another particle that we now have to go look for. And so thus the Axion was born. And for anyone who's curious about the nomenclature, Frank named it after laundry detergent. So that's where the Axion comes from. So for those of you who are familiar with the Axion, or when you're dropping your research program and reconfiguring, you might read about thermally produced axions. Those are not the ones that I'm going to talk about today, but they are indeed produced in stars. And for the purpose of today's talk, these are chargeless. So these are always chargeless particles, but for today's purposes, they're 10 to the minus 5 electron volts in mass. And the theory doesn't tell us a priori what the mass of the axion should be. I don't particularly think we should hold this against the axion, since we also don't really know a priori why the electron has the mass that it does, or say the Higgs. So the axion's not particularly problematic in that sense. And importantly, they are essentially spin-zero bosons. They are actually pseudo-scalars, but that's a technicality that doesn't matter so much for this talk. And that's going to turn out to be important. Oh, the other reason we picked this particular mass is just because it made it easier to compare with the rest of the literature. And also 10 to the minus 5 electron volts is a very nice mass for matching with cold dark matter. So you might ask, okay, it's all well and good for you guys to push particles around on potentials and do calculus, but at the end of the day, we would like some actual physical products. So the Axion dark matter experiment, which is physically housed at the University of Washington Seattle campus, is indeed actually hunting for the Axion. And so what you see here is the Axion mass on the horizontal, and the vertical is its coupling to strong magnetic fields. So the reason that we can go out and do a direct detection experiment with the Axion is because axions will couple with strong magnetic fields, and this will produce photons. It is worth saying that the mass and the coupling are not linearly independent of each other. So that's one reason you kind of see this linear line. And you can see a planned timeline for when they expect to scan through some of the parameter space. And I won't say anything about why there are bounds from stars, but if somebody wants to ask me later, you can. So I emphasized that axions are spin-zero bosons. They're scalar particles. And I was asked a very good question earlier today. Does it really matter whether the dark matter is a fermion or if it's a boson? And so in fact, it may actually matter. So just to kind of remind people of why we might care about this. So fermions, if they are fairly warm, are just going to show a classical thermodynamic distribution. But as you cool them, they start to show their true nature as stacking particles or ladder particles. They cannot all share the same energetic state. Bosons, on the other hand, while looking basically the same as fermions when they are fairly warm, as you start to cool them down, are much more kind of like a hive mind particle. So they can all share the same low energy state. And as you get colder and colder, you will see almost no distribution, and they will all be able to drop into the same ground state. So this is something that's not possible with fermions. So a very natural question to ask is if the WIMP, which is on the Venn diagram to end all Venn diagrams, basically the entire supersymmetry bubble that went across here, is there a difference phenomenologically between these WIMP candidates and other scalar candidates? And in particular, how does this manifest for the axion? And you might ask, okay, well, why would you care so much about the Axion in particular? And the reason is that unlike, I could go to a chalkboard right now and write down a scalar particle and call it the Chandion or something like that. But what distinguishes the Chandion from the Axion is that the Axion is actually needed to resolve an issue in the standard model. We cannot go without solving that strong CP problem. And so it is worth understanding what is the phenomenology of that particle in our universe. So you can actually see the phenomenon of this Bose-Einstein condensation in real data. So this is from the Gila experiment in Colorado. So this is rubidium-87 in velocity space. And you can see as you get below something that I'll call the critical temperature, and I'll explain what that is in a second, you get this spike that goes from a thermal distribution to a very nice spike. And then the spike gets thinner as the temperature gets colder. So this is a Bose-Einstein condensate. And essentially, the particles are acting like one superatom. So another way of thinking about this is at higher temperatures, pretty much any type of particle is going to act like a billiard ball. They're going to bounce off of each other. As you start to cool down to lower temperatures, the particles will start to act like individual little de Broglie wavelets. As you get to the critical temperature, these will add together coherently. So this is one of the most important characteristics of the Bose-Einstein condensate, is the coherent matching of the waves. And then if you are able to get to absolute zero, you can get this perfect, beautiful, coherent wave. So these are Bose-Einstein condensates. These are some of the most amazing things that I think we've ever been able to create in the laboratory. I don't know, maybe graphene has kind of taken over that slot. And it's usually thought of as a lab phenomenon. So I think it's very easy to be skeptical about why any mention of these is appropriate in a talk about early universe cosmology or particle physics or cosmology in general. So I would like to make a couple of suggestions of ways that you can think about it. So I think there are two things. So you might say, oh my gosh, that's a lab experiment. It was very, very hard to do. It was so hard to do that people won the Nobel Prize for doing it. So I think one, we should not mistake what is hard for us as being hard for the universe. The universe is apparently much more competent at making things than we are. And that's not at all to say that it was not a significant achievement to do it in the laboratory, but the universe is often able to do things that we can't, like make stars. That's pretty awesome. The other thing is if you ever see any of the people involved give a talk about this, they'll tell you that 75% of what is hard about making a Bose-Einstein condensate in the laboratory is getting the temperature conditions right. Getting the laboratory cold is extraordinarily hard. And this comes down to figuring out how to get yourself to this critical temperature that I mentioned. So the critical temperature at which point a Bose-Einstein condensate will just happen is given very nicely through a relation with the particle number density and the temperature. And this exponent right here, this 2/3, so this is specifically, I think, for a potential well. For a 2D potential well, I think. This exponent is going to be set by the potential that you are in. And so there's a very straightforward way of figuring out what the relation between your temperature and your density should be, but then actually getting down to that temperature, given the densities that we are capable of creating in the laboratory and controlling, is going to be the hard part. So the next comment that I will make is that so this is so much worse because I forgot my laser. But usually I have a laser when I give this example. Lasers were something that were considered very hard to make, very difficult to produce in the lab. It was considered a significant achievement. People won the Nobel Prize. Now, any postdoc can afford enough lasers to the point where she can just lose one and not be super worried about it, right? And so this is another example of something that we thought was very hard to make in the lab, and then with time we got better at it. And it's also something that you would expect, okay, that's so hard to make in the lab, I would never expect to see it in space. But anyone who has done radio observations of the Orion star-forming regions knows that there are beautiful water masers in that area. And so that's an example of a radio laser that is naturally occurring. So I think that there is good reason to consider the possibility that this is yet another interesting atomic physics phenomenon that could be occurring naturally in the universe in general. And in this particular case, it gets even more interesting because it's not actually happening with atoms, but rather with particles.
So if you were to be asked what you are, what is the general definition of a Bose-Einstein?
Ooh, that is actually a question that even the atomic physicists would not give you a clear answer on. So.
I don't know. In fact, I don't even think they think about it, right? What they do is they say the Figma distribution function. They try and diagonalize it to go to the lowest highest score, depending on how you want to talk about it. And really what it is that you have a separation between higher momenta and low momenta.
Yes.
And that is actually ubiquitous in nature, where you can have low momenta. So this is a challenge. Let me say that in some real respect, an ordinary star is a condensate because it's got the low momenta associated with the structure of the density that you look at. And then there's the high momenta associated with the thermal processes. But I completely agree with you. I put it to the experts in the subject. And all they do is they give me this lowest mode argument of psi star psi, where there is you do the positional separation and then you look for the lowest mode. But that actually is not even true for any Bose-Einstein condensate because they always have structure.
Always have a distribution.
So they are not k equals 0 like you learn in the textbook.
So there are some nice discussions, and of course, the name of the particular Nobel laureate is escaping me right now. But there is actually a textbook that has a very nice discussion about the different definitions. My personal favorite, just since we're on the topic, is the off-diagonal long-range order. I think it's a very nice way of defining it because then you can just pick the eigenvalues off the matrix. I'm going to get to why this conversation is a little bit complicated when you're talking about the axion, because there are some things, the axion is not an atom, and it's notably important that the axion is not an atom. But I agree with you, it is a little bit of a complicated question that I think gets worse when you're trying to talk about it with particles. Okay. So I think that we have established that what a Bose-Einstein condensate is, and B, that we probably don't know what a Bose-Einstein condensate is. Okay, so on to the question of Bose-Einstein condensates in space. So this is actually something, I'm not introducing you to an idea that is super fresh in cosmology, in the sense that many times over the years people have asked the question, can scalar particles produce a Bose-Einstein condensate? Can a scalar dark matter produce a Bose-Einstein condensate? I'm going to talk about one particular proposal that led to us kind of coming up with a counter suggestion. So Pierre Sacchivi and one of his students proposed in 2009 that axion dark matter must form a Bose-Einstein condensate state during the radiation-dominated era. And this was an interesting proposal for a few reasons. So one, the numbers kind of check out, although nobody has actually written down what this exponent should be for gravitational potential. That's worth throwing out there. But we're in a very high occupancy regime with axions if it is the dark matter. But what was interesting and different about their proposal is that they suggested that the axion would thermalize into a Bose-Einstein condensate through gravitational thermalization and not from phi-to-the-4 self-interactions, which is what people have previously traditionally studied with scalar particles. So the second claim that they made was that the Bose-Einstein condensate has what they called a correlation length, what you would see in the atomic physics literature as a coherence length, that is Hubble scale. So Hubble scale for the radiation-dominated era, so not quite our Hubble scale, but needless to say, that is still a large claim, even for the radiation-dominated era. And so people who are not familiar with this kind of work might ask, well, why would we pay so much attention to this? So I'm one of those, for the sake of completeness people, we should check it, see if people are right. But it's also the case that Pierre Sacchivi is the first person who noticed that the Axion would make a good dark matter candidate. And he was also the first person who noticed that we could do direct detection using the Primakov effect. So he has at least cost the United States government, what was the last, ADMX got $36 million. He's cost us a lot of money. So that's one thing. But it's also the case that he has often said very, very smart things. And so we were very curious about whether this was the right way to think about how the Axion would behave in the early universe. So these are this is the PRL and then the longer paper. And I do think that they are worth looking at. Importantly, this has an observable attached to it, this particular perspective on the Axion. So one of the claims is that there will be these caustic rings, so these regions of high density, and that they will have a ring-like structure, which you do not always see with WIMPs. And so this is tens of kiloparsecs across, by the way. So this is basically galaxy scale. So this is actually something that people could go out and look for. And I'll just mention really, really quickly, there's a postdoc named Julie Dumas, who's now at Vanderbilt University. And part of her dissertation work was actually comparing rotation curves with, and halo models with Sacchivi's picture. So I actually think that she's interested in continuing this work. So if anybody is interested in it, she's definitely the expert to talk to. And I think this appeared in AppJ in September. So we were intrigued by this claim about the long coherence length. And we weren't sure that that felt intuitive, although you could say, well, what about any of this would feel particularly intuitive? So we asked ourselves, do Axion Bose-Einstein condensates with long correlations form? And we wanted to see also if we could come up with our own way of doing the calculation, because I feel we are fairly smart people. We had a difficult time following the calculations. So we thought maybe we will try and come up with one that we can understand. So we realized that one difference is that we could describe the condensation in the high density regime with a classical field theory because we are in a high density regime. And this is one difference with the way that Sacchivi and Yang approached it. A personal goal for me, I realized that one day, knock on wood, I guess. I don't know if it's kosher to be superstitious in a science talk, but okay. We are going to find dark matter, and we are going to have to tell our students about it in their statistical mechanics classes. We're going to have to tell them, this is what the dark matter does. This is how it behaves. And so I was fundamentally interested in understanding what is the impact of gravitation on the statistical mechanics of the Axion, or in scalar particles in general, but we can start with the Axion. So what we realized, and this is kind of a way of putting it to help you remember, that as with people, it matters whether particles are attracted or repulsed by one another. So that's your takeaway from this section of the talk. A more technical way of putting it is that the sign of the interaction is going to determine the correlation length. So it depends on whether you're talking about the Axion, and it depends on whether you're talking about gravitation or some kind of repulsive interaction. And so this is in our paper. There's also a PRD version, but they're identical. So when I first started thinking about this problem, so let me start by saying Mark promised me that this would take 2 weeks. It actually took 6 months. And the first thing that I thought was, like, obviously, we don't need to solve this problem. It's in a condensed matter or an atomic physics textbook somewhere. But there are some important differences I realized almost immediately. So one, atoms experience repulsive forces that axions don't. We also control the trap and the potential in the laboratory and when we're doing very simple calculations. And gravity is essentially never relevant on laboratory scales other than trying to get things to fall into your trap. That's really when atomic physicists use gravity. The time scales involved might be different, and then there are a host of other things that we may not appreciate about the difference between axions and atoms. So, a very important point about the axion is that it has an attractive self-interaction. And this is why I am so picky about the nomenclature, because if you go into the literature, some axion-like particles that people are writing about have repulsive self-interactions, and some of them have attractive self-interactions. And as with people, it matters whether the particles are attracted or repulsed by one another. So it really matters whether you're talking about the QCD axion or something else. Okay, so this is mostly for the sake of completeness for anyone who wants to actually see that it's an attractive interaction. Occasionally, someone is really quick on their Taylor expansion feat and notices it's a little bit weird that there's a minus sign there. The minus has not been disappeared. It's down here. This is just a thing that happened in the literature at some point. I don't know why. Since we're in the non-relativistic regime, we can treat this as a complex scalar field. And really, all that I want you to take away from this is that even though we are still treating the system classically, this actually looks very familiar. So if you ignore these two terms, actually it's nice using a ruler. So if you ignore these two terms, you have Schrodinger's equation. And if you ignore this term, you have something that's called the nonlinear Schrodinger equation, but is also known in the atomic physics and condensed matter world as the Gross-Pitaevskii Equation. And this is actually the very equation that is used to describe Bose-Einstein condensates. And so you can see very naturally how that phenomenon becomes more mathematically evident. And then, of course, we added in gravitational interactions. So then, of course, the question that was so astutely brought up earlier is really what happens when the lowest energy state separates from the higher momentum states and all of the particles go down into the lower momentum state. So another way of doing this, if we ignore the self-interactions, you can look at our paper and we talk a little bit about why we can. If you minimize the Hamiltonian for the gravitational potential, you find that the characteristic energy state is interesting. So the first thing that's interesting about it is that it's not 0, which is usually what you expect for an atomic system, that the lowest energy state is actually going to be the k = 0 state. And what's interesting about this, so it's nice to see this graphically, is that when the interactions are attractive, the characteristic wave number is going to be non-zero. And this means that the correlation length is going to be finite. When the interactions are repulsive, you will have k = 0 ground state, and you will have a long coherence length. And this is really just a matter of what is an attractor configuration for the system and a non-attractor configuration. So this is the second time I'm using the word attractor, so you start to see that there are some patterns in the kinds of things that I'm looking for. So what does this really mean? To get a feel for this? Attractive interactions are going to give us clumpy things that have come to be known in the literature as Bose stars. This is a little bit of a misnomer because they don't radiate. They pretty much don't do anything that stars do. There's no nuclear reactions, nothing. Star just means clump of stuff, basically. So we could have called them Bose planets, I guess, or Bose asteroid would actually have been more appropriate. And these are compact phase correlated objects. These are macroscopic quantum states. It's pretty cool. You just think about macroscopic quantum states floating around in space. So the other cool thing about it is that it turned out that there was kind of a convergence in the literature where a lot of people were running into similar phenomena by asking questions that were similar to ours, but not quite the same. So this is from a paper in 2014. Interestingly, this is from a paper in 1999 by Klebnikov and Kachev, where they asked essentially the exact question that we asked, not about gravity, but about an attractive interaction scalar field in a phi to the 4 potential. And what they found also is that clumps would form. As you evolved them in time, the clumps would merge. But the clumps, while clearly self-coherent, were not coherent with each other across space. And so you see a local coherence, but not a large-scale, long coherence. So depending on the axion mass, the objects that we're talking about, and we're talking about a highly idealized situation. I don't expect it to come out quite like this in the numerics. Are 10 to the minus 10 solar masses. So this is about 20 times the mass of the asteroid Ceres. And with a coherence length of about 1 kilometer. So these are not very large objects. And they are forming in the early universe. So I want to be clear that I am not necessarily suggesting that I expect that we can go out and find one today. I think that there are some very serious questions there about what happens during structure formation. And they're kind of tricky to answer because right now n-body simulations often use particles that are much bigger than this. And so it's kind of a tricky issue. I was not one to give up on the question of what we could learn from atomic physics. So I actually, even after we figured this out, went back and said, but in atomic physics books, I never really read anything about attractive interactions. And it turns out that the reason that I hadn't really in a lot of the classical texts is because they, generally speaking, thought that they weren't very interesting. It was expected that they would not be stable, that attractive interaction Bose-Einstein condensates were not where the exciting action was at. Nonetheless, in 1997, a couple of years after the first BEC was formed in a lab, somebody tried it with lithium-7, which has a negative scattering length. And they found that, in fact, you could form a stable Bose-Einstein condensate, but they were size limited. If you put too many atoms in them, they collapse. The question of how many atoms was actually tricky because it turns out it's hard to take pictures of these systems. So it might be 1,000, it might be 10,000. There was some back and forth in the literature, and I am not an atomic experimentalist. But the important takeaway was really that these were size limited. And so we actually do see a similar phenomenon in the atomic physics world. There was also a paper in 2014 by Ebbe. Josh Ebbe is a graduate student at the University of Cincinnati, where they used a completely different calculational technique than we did and came up with an answer that was within a couple of orders of magnitude of us for the scale of the clumps. And so that made us feel confident that we were going in the right direction. So just to back up and look at the big picture, so we expect that the axion field is going to evolve the way we expect fields usually to in a Hubble background. Then we expect that the system will try to thermalize. And for repulsive interactions, this will go the way that we usually expect things to go. But for attractive interactions, does the axion dark matter form Bose-Einstein condensates? Yes, we think so, in small, locally correlated clumps, such as Bose stars. So there's clearly a lot of questions here. I think that they are very interesting. So the one nice thing about the Ebbe group's paper, and they've put out some subsequent, is that their calculational technique allows them to check the stability of the system. So how big can you make it before it collapses? We are working on some numerical scalar field calculations with Tom Giblin and Julian Blumfield, along with Mark Hertzberg. There are some interesting questions about microlensing here. I know that there have been some limits set by Kepler, but they don't necessarily rule out the presence of these objects. And then I have been kind of interested in, could you get one of these in a giant magnetic field? So basically, could you have an ADMX in outer space? So that would be pretty exciting if we could figure out how to find it and it had a strong enough signal. Then there are also questions that are motivated by the fact that in string theory, there are lots of axion-type fields. So what are the dynamics like if there are multiple axion fields? And then also, what is the actual timeline of this dynamical formation process? So I think understanding the origin of particles requires ideas from across physics, and I hope that's become somewhat clear. Because just to kind of really give the big picture, we are trying to figure out how to go from these very maybe bizarre ideas about like stringy space-time or a quantized space-time to we actually believe this, that like at some point our universe was just fields falling down on potential wells and that that's still kind of what's happening. And that somehow we get from that little grid picture to this, which is actual SDSS data. So I think we are just beginning, but this is the end of the talk. So I think that there are lots of interesting calculational things happening in addition to the actual physics. And I also think that there's some fun phenomenology with Bose-Einstein Condensate, Axion, dark matter. So everybody's going to drop their research programs and work on this now, right? Yeah, OK, thank you.
I still don't see where solar masses came from. And it's sort of hard to comprehend how in this incredible environment where there are axion FF dual type terms that you would be able to form a condensate into parts for example, interaction.
So I think it's, so this is also, I guess I'll go backwards. As far as the stability of the condensates in a dynamical environment, this is happening early enough in the universe that I'm not sure that we have to worry too much about baryons, but I also... So this is going to be later than that, unless you're thinking about like initial conditions with domain walls. Oh, okay. Yeah. So you're thinking about magnetic fields. Yeah. So I think that's an interesting question. I don't know the answer to that question. So to answer your first one, it's pretty clear in the paper. So I'm happy to come talk to you about it and show you.
I mean, so is it not only in the context of the expansion of the cosine potential, or is it actually done with the cosine potential to show that?
No, it's the phi to the 4 expansion. So we drop the higher order terms. It's done as a phi to the 4. There's actually also, since you brought it up, I might as well tell you the other weakness, which is the axion is a real field, right? And real fields don't have a non-relativistic limit. And so we had to make some arguments about what we thought what the non-relativistic limit would look like. And so we do discuss that a little bit in the paper about why we can ignore the number violating processes. So that's kind of, and that's actually something when I went to visit Cincinnati and talked to the group there, we had some back and forth about whether we were really allowed to do that. So I think that there are still some technical questions there. And I think like if Pierre was here, he would be jumping up and down and saying, they can't treat it as a classical field, you have to treat it as a quantum field. So there's diversity of opinion on how to do that.
Can you just talk a little bit more about the timescales that you expect that, like the clumping to happen on?
So
kind of an arbitrary time on those plots that you showed. It's like t at 0.2 and then 1. So.
Which one are we talking about? I was going to say, I put a time on any of these?
Yeah.
Oh, yeah. OK, so actually that's a good question. I don't remember off the top of my head anymore what time scales that they used. I will say that I think that this result, the only thing that the timescale is really going to give you is what the mergers of the clumps are. Maybe one interesting thing that I will tell you about this paper, because I now realize that I didn't mention it, where time might get more interesting, is that even though in these pictures you're seeing the clumps, something that they didn't show in these images, because it would be messy, is that there's also an ambient gas of particles that did not go into the clumps. And they had the idea, I don't know where they got this, to vacuum the gas out of the box just to see what would happen. And they discovered that the clumps would evaporate particles to repopulate the ambient gas. So this was a 64 cubed particle simulation, which in 1999 was not terrible. Now we would expect people to be able to do a lot better. So it's not clear whether that's a product of the numerics or if that's an actual, what they called a potential, quasi-chemical equilibrium of some kind. But I think it's interesting. So I quickly went through it on the slide. But one of the questions that I've been interested in is whether there is an evaporative cooling-like process happening where, because axions don't radiate as the thermalization is happening, particles are getting kicked out, kinematically warmer particles are getting kicked out, and that may in fact be what that equilibrium is. And then I think you have to start worrying about time. That said, I actually think that like the EBI technique, maybe for that particular question, has better capacity than ours does for answering that question. We were initially not planning to discover a potential phenomenology. We just wanted to know if the coherence length was long or not. And it kind of grew from there. Yeah. I don't know, sorry, it took a while to answer that.